So welcome to lecture 13 of MCS 471 on numerical analysis, or in this sequence here of lectures on numerical linear algebra. So in this lecture we return to iterative methods to solve linear systems, but now in connection with optimization problems. So we will see that gradients occur when we solve optimization problems, but also Jacobians and Hessians. So there are three parts in this lecture. One could say that we are going to work with gradients in the first part. In the second part, we're going to define a multivariable version of Newton's method, and they're the Jacobian method. Positive definite matrices, and these matrices occur when one applies Newton's method to finding critical points of a vector, or actually of critical points of a function in several variables. The Hessian is actually the Jacobian of the gradient vector. All right, so let's dive in. So we will see how linear system solving connects with optimization. So in the last lecture, we seen how a positive definite matrix, actually here it's still a positive semi-definite if you allow equal signs here, but in short, every matrix leads to a quadratic form if it is symmetric and positive definite. So the symmetry is that when you transpose, you get the same matrix back. Now let's look at a very particular quadratic form. It's given here by this Q. Now if you look at the gradient, if you look at the vector of all the partial derivatives, where Q of x equals 0, this is when you have that ax minus b equals 0. So now we have a quadratic form, specific quadratic form, defined by a matrix and a right-hand side vector. The connection between optimization and the solving of the linear system is that if you compute the optimum of the quadratic form, then actually you are solving the linear system. So one could interpret this as an application of linear system solving in the way I just explained it. You take the derivatives of the quadratic form and you get a linear system. So any quadratic system, quadratic form will actually lead to a linear system. So we will not do that. Instead, we will use ideas of optimization to get to a method for solving a linear system. So we will introduce, so here is another way of seeing this. If we introduce a different norm, so we have the norm that has a subscript, the matrix, then this is defined as this. So if the A is the identity matrix, then we actually get to the square of the Euclidean norm. So why do we do this complication? Well, look what happens. What happens is that when you write it out in great generality, we see that we get the quadratic form back where we started with. So our special quadratic form Q is actually equal to our norm, our A norm. Our vector norm that uses the positive semi-definite matrix A. So another point of saying that if you want to minimize the quadratic form, and we are going to minimize this quadratic form to solve the linear system AX equals B. So if we can minimize the error term, then actually we are minimizing the quadratic form. So one natural algorithm to minimize a general function is to use the steepest gradient. So you compute the gradient at a point, and then you go in the direction of that gradient. If you look for a minimum, you go for the steepest descent. So we will consider a method, an iterative method, that is very similar to the steepest descent. So the steepest descent is a very simple method, but we will make it better, and that will lead to the conjugate gradient method. So we start out here with 0. In a way, this is kind of the generic starting point, but in many practical applications, we actually know already a good start for our solution, and we will compute the residual. So here you see that if the residual is smaller than our epsilon, we actually stop already. So the first stop criterion is taking the norm of the residual. So we will have a direction that is P. So we will walk into that direction. So here is the resemblance with the conjugate gradient, with the steepest descent. So we have a vector, and we take a step in that direction. Then we update the residual, and then we also update the search direction. Now, this algorithm depends on two critical quantities. So we have the step length, and then we have the improvement of the search direction. So we have an alpha and a beta. And in what follows, I will try to explain the formulas. Why do we take the alpha and the betas like the way we are doing? We have seen that last time that Koleski is actually twice as fast, at least twice as fast as the LU factorization, but it's still a cubic method. Here it's an iterative method, and iterative methods, when they converge, they have the promise of working with a quadratic cost. So the cost of the exercise, the goal of the exercise 1 is to analyze the operations that are done in the execution of this algorithm. So one does a lot of, and doing this with a general, for a general dimension. So you see that there are a number of multiplications. So here what I'm underlining now, perhaps I should have taken another color. I have A times the search direction, and the A times the search direction comes back in. So we covered iterative methods before. What iterative methods are doing is that they're doing matrix vector multiplications repeatedly. And I just circled in green the bottleneck. So my mathematical description does not use a separate variable for the A times P sub K minus 1. But you could say that you do this only once. So in every step here, as it is written now, we do two matrix vector applications. So the cost of every step is therefore at least quadratic in the dimension. But if you look further, so what then remains, so other than the green circled computation here, either we multiply a vector with a scalar, or we do the inner product of two vectors. Or we do the product, so the inner product, if you store actually here the A times p sub k minus 1, what is here in the denominator, is then again an inner product. And inner products are linear. So in solving this exercise, you point out that there are two matrix vector multiplications, and then there are a number of inner products and products with a scalar, which are both linear in the dimension. So the justification is important. So coming up with a neat expression, and n will give you perhaps some credit. So you can already write that it is quadratic. So the one step means that you ignore the 4. So it's actually what is here in the body of the loop. One step of executing the conjugate gradient method. So this is the motivation. So we can solve very large problems still within a reasonable amount of time. So cubic algorithms do not scale very well once the dimension gets past several thousands. All right, so I try to explain what the algorithm was doing. So here is a more informal description. So we have three main vectors. We have the residual vector, the vector of the current approximation, the x sub k, and then we have the direction. So these are our three main actors, and they are changing. So the first vector is perhaps easiest to understand. The first vector, the r, is the residual. So this is also known as the backward error. How much should you change your problem? And in particular here, the right-hand side, vector b. So the computed vector is an exact solution. So the second actor is then our vector that we are updating. So here you see the update, very similar to the steepest descent method. And then we have the vector which is the direction of the update. So these are the three main vectors that are updated. We can already observe a relationship between two consecutive R vectors. So the R naught is obviously the residual, but it's not actually obvious that any other R vector is also actually a residual. Well, this relationship actually makes this clear. If you substitute the definition of xk back in, and then you also use the definition for the r sub k minus 1, so the previous r vector, then actually you see that there is a very neat relationship between two consecutive r vectors. And here this is made more explicit, so you can actually, because of this relation, you can see that all the r vectors are actually the residual vectors. So they measure the proximity of the solution, the computed solution, to the exact solution. So that's our first important relation on the vector r. So let's now look at how do we choose the step size? How do we update the solution vector, the approximation for the solution vector? So let's look at the property actually that we want. We want that the update vector is orthogonal to the residual vector. So orthogonality will play an important role in the remainder of the course. We care about accuracy. So orthogonality will help us a lot to ensuring orthogonality. So here we will use the orthogonality to indicate that the residual vector and the update vector must be perpendicular to each other. So that's an important criterion also that we will use later whenever we get to the least squares. So by this condition on the fact that the update vector must be perpendicular to the residual vector, we obtain the expression for the alpha. So first we do rewriting to get from the xk, we get to the rk. So we actually are at the left here computing the residual. At the right, we see what happens here. We actually then get a relationship between two residuals vectors. So we want that the rk is perpendicular to the vector, and this will lead to a condition on the alpha k. So the condition that we impose on the new direction will actually, if we use that update direction, then actually we have an explicit formula for our rk, for our alpha k. So that explains one thing or another thing. So we use the orthogonality to rewrite. So we can rewrite the rk a little bit better. So as you see here in the numerator, we still have the pk minus 1. Well, we can replace the pk minus 1 of the numerator by the residual of the previous step. Why do we do this? Well, it's a nicer expression, but if you think about the first exercise, it may actually also save us some time, because note that this is actually what you use, this inner product is what you use in the 2 norm. So in the first exercise, you had to compute a 2 norm of a vector. And for the 2 norm, actually, you get the inner product of the vector with itself. And here you can see that you can recycle that. So we can rewrite the numerator using the expression for the update of the direction vector. So, and we then also use the orthogonality to rewrite the relationship. So we actually do have that because this is 0, we actually also have the orthogonality property. Okay, so this gives us a neat expression for alpha k. Now, where does the beta k comes in? And this was also to explain how the name of the conjugate gradient. So we had this more complicated norm where we use the A matrix. We actually have now that the directions, the gradients are actually conjugated to each other. They are related. So conjugating is a little bit more fancy word for relations. They are related to each other by this matrix A. And by actually by enforcing this new condition of the conjugacy, that will lead us to an expression for the beta. So the beta that then here still has this matrix vector product in its numerator. So this can still be simplified by using again the orthogonality. So, and that gives then the expression for beta k that was used in the mathematical description of the algorithm. So in the little slides that I have used here so far, I've tried to explain the algorithm in kind of in a backwards manner. So we started with the formulation of the algorithm, and then we're going to derive essentially the algorithm. So there are some key parts in this. The algorithm will actually ensure that the residuals are orthogonal to the update vectors. That gives them the formula for the alphas, for the step length. And the other condition is that we do have this pairwise conjugacy on the direction vectors. You also actually now recognize the condition that we used to minimize. So actually we were minimizing the norm of E, and that was E transpose times A times E. So that's the square of this special norm. And you see that this is what we want to minimize. And we actually also want that if you, why do we actually do this? Well, at the minimum, everything is actually zero. So the directions in which we have to go, there is no other direction to go. We are already at the minimum. So that's why we actually enforce this condition of directions. All right, we define our algorithms by Julia functions in this course. So we will have a conjugate gradient method, which has 6 arguments. So here my documentation string leaves off actually the default verbose option. So there is an extra verbose option. So it's an iterative method. In addition to providing the coefficient matrix and the right-hand side vector, the user must provide a start solution, start vector. If you don't know anything, give 0. That is as good a start vector as any. So we have default tolerances, default tolerance of 10 to the power minus 8 and 10 iterations. That's because I tested this on very small examples. All right, then we start out with the initialization of the x, which is now actually called sol. We have our residual and then our direction p, which will be initialized to the residual. So this is no longer a mathematical algorithm. We will have only one solution, only one residual vector, and only one direction vector. So typically we have our stop criterion at the end, but here you see that everything is actually now at the beginning. So we have our stop criterion on the number of iterations, and we have then the stop criterion on the residual, which is the norm of the residual vector. So the algorithm starts out like this now. And then we have the printing. So we actually will print out the values for the coefficients alpha and beta, because they actually should go to 0. So that's actually an important property that I forgot to point out. The alpha and the beta have both in their numerator the residuals. All right, the algorithm, so here it is actually. So here you see the numerator for the alpha. You also see the numerator for the beta. So when you see that they both have the norm of the residual sitting in there. So actually all these numbers, so the sum of R, the alpha and the beta, they should actually all go to 0 if we have a converging process. So in a way, you could interpret this conjugate gradient method as kind of an elaborate way to check in 3 different ways, actually, are we actually there yet? So, and it's very, very small. If your step size get very small, then actually you are already very close to the. So I'm sorry, my internet was a bit unreliable. So let me redraw it again. So the delta x is actually here the alpha times p. Then actually you can see we have only, this is a residual oriented algorithm. So the alpha is actually directly proportional to the update, the size of the update. There is the update of the solution, and then there is the update of the direction. That is for which the beta coefficient is being used. So it is a very simple algorithm, simple enough to work on very high dimensional problems, many equations, many variables. But we do this here on very small systems. Here I have a very small example that fits at in one slide, so executed at the command prompt. And you see that we actually are converging extremely fast. So in actually a couple of steps, in 2 steps, we actually have success. All right, very good. Here is another exercise. So this is an exercise which still is for a small dimension. So we will look at increasing dimensions. So you execute these statements. Note the way how the matrices are formulated. So this is an optimization problem. We are applying a variation of the steepest descent method. And when will this work well? When our quadratic form that we will minimize will actually work on a positive definite matrix. So it has the same convergence conditions as we assumed for the Cholesky factorization. So you can actually consider, we have seen the methods of Jacobi and the relaxations of Gauss-Seidel, which were kind of the iterative variations to the direct LU factorization. We have the direct Cholesky factorization, which is a direct method, not an iterative method, which works well for positive definite matrices. Here we have the positive definite version for large problems. Now here I'm generating my positive dimensional matrices, my positive definite matrices in the very straightforward way. By the end of the last lecture, we saw that that was actually not such a good idea. So in a way, this exercise is mainly to investigate the convergence. So see how it converges. And the convergence should happen because these are still very nice positive definite matrices. All right, we've seen gradients, so let's now move on to Jacobians. So we've covered Newton's method to solve nonlinear equations. Let's now look at the more general case, and let's look at a system of 2 equations in 2 variables. And in an iterative method, we like to compute updates so that we are closer to the exact solution. So the system is given to us with variables x and y. We have somewhere a first approximation for the solution, so x naught, y naught. First of all, we check whether it makes it 0 or not, but most likely, otherwise we wouldn't really have anything to do. So we will compute a delta x and a delta y so that we will get closer. So we actually reformulate the original problem into a problem where the unknowns are actually now the delta x and the delta y. So we have two equations in two unknowns. Why is this a simpler problem? Well, we actually hope that the x naught, y naught is already close. Then actually we are looking for small numbers, delta x and delta y. So now how do we compute this? Well, the delta x and the delta y are small. That means that we can apply Taylor series. So Taylor series, we have seen, were an alternative way to derive Newton's method. Newton's method is also called the tangent method. In a way, we could also give here a geometrical interpretation by using the tangent at the intersection of the two tangent planes. So in 3 space, we have two tangent planes, and two planes intersect in general in a line. So the two tangent planes will give us the tangent line. And you could interpret also the Newton's method geometrically. So it would be a very good exercise. I haven't done this yet, to actually give that geometric interpretation. But we will work with Taylor series in several variables. So now we need the partial derivatives, which we remember from calculus. You take the derivative with respect to one variable, treating all the other variables as constants. So we ignore the higher order terms. So the dot here contain the delta x square and the delta x times delta y and the delta y square. Because all the delta x's and delta y's are actually small, we can do that. So we actually will truncate those. So forget about the dot. And what is the punchline now? This is a linear system. So this is why Taylor series are so very powerful. Locally, everything is reduced to a linear system. It's not obvious from here. So this looks like a problem with a lot of letters, and it's important to realize that delta x and delta y are actually the two variables. And we will formulate this now as a linear system in the proper notation using matrices. So I've copied still with the dot of what I had in the previous slide. So what do we know? Well, we know the x naught and the y naught. And what we actually did, as I said, we evaluated. So we evaluated the x naught at f, x naught, y naught at f, and at g. And that will actually make the right-hand side. So it's not 0, so it has here a negative sign, because we want to solve this equation for delta x, delta y. So then what we also know are actually the values of all the partial derivatives. And that will be the coefficients in our matrix. So what we don't know are the delta x and the delta y, and that will make our update vector. And actually, we solve one linear system, and the linear system will actually give us the correction terms to the current solution. The magnitude of delta x and delta y of that vector will actually give us an estimate for the forward error. So in a way, if you look at this formulation a little bit carefully, so at the right-hand side, we have the backward error or the residual. At the left here, what we want to compute, we actually have the forward error. So you can also see Newton's method as a method to try to connect forward error with backward error. All right, in general, we have a system of n equations and n unknowns. So for this lecture, n is still equal to m. In later in this course, we will see that n can typically be more than m. But in great generality, we have the matrix of all first-order partial derivatives, and that is called the Jacobian matrix. And that's a matrix, a genuine, so here it is formulated as a matrix of nonlinear functions. So you can see this also as a function of a vector that returns a matrix. So for any value of the variables, the x variables, you get a matrix back. So this gives us the coefficient matrix. So you see the indexing, first row deals with the first equation. So the second column here deals with the second variable. So there is a very natural way to order these elements in the Jacobian matrix. Here is an example, a numerical example. So we have a nonlinear system, but still a nonlinear system where we actually know the exact solution. So we compute the Jacobian matrix, and then we compute the updates by solving a linear system. So this is a numerical example dating from the time of the scientific calculator. All right, so we are going to implement this in Julia using Sympy. So generalizing here to two variables. So it would be an interesting exercise, but that's an exercise in symbolic computation to make this work for any number of equations and any number of variables. But we do this here in two variables, generalizing the functions that we have covered when we first introduced the Newton's method. So our expressions are given as strings parsed into Sympy expressions with Sympify using the global definitions. So the Sympify works within the global context where the x and the y are variables that are occurring in the strings. Once they are Sympy expressions, we can evaluate and, more importantly, differentiate them symbolically. And we lambdify. The lambdify actually will return functions. So we have the expressions for the derivatives, and they are turned into functions. So we will actually have a matrix of functions that we can evaluate. So this is what this essentially very simple function is doing. It takes strings on input and it returns a function to evaluate the Jacobian matrix. Here you see how this then actually happens. The lambdified expressions can be evaluated numerically. So, and we return a matrix. So this is here, everything is happening here with the 64-bit representation, with the 64-bit floating point numbers. All right, so these are the auxiliaries. And now we can define Newton's step, one Newton step in great generality. So what we are having on input are the vector function that evaluates the nonlinear function, and then we also have the Jacobian function, and we start with the current point. So this is extracting the body of the loop in an iterative method by a step function. So in a way, sometimes it's confusing to think about the entire iterative method. Well, first isolate a function that computes the next point in the iterative method. That's what this Newton step is doing. So, and here comes the linear algebra, and the linear algebra is entirely encapsulated by the backslash operator. So we use the built-in linear algebra module built in with Julia, and we compute the update by the solving of a linear system. Then what we return is the next two values plus the norm. So here we have the estimate for the forward error and the estimate for the backward error. So for well-conditioned problems, if everything runs well, they are of the same magnitude. When the backward error is small, also the forward error is small. So we have the next point in the iterative method and two quality and two floating point numbers that will tell the quality of the approximation. The estimate for the forward error. So this was here the delta x, its norm. And we have then the norm of the residual. So the residual was b minus a times x in linear algebra solving. Here it is the residual, which is the norm of the function evaluation. All right, so then we have the iterative method, where we will have again quadratic convergence. We do not allow that many iterations. If we require a 10 to the power minus 8, we only allow 5 iterations because we expect quadratic convergence. So the default tolerances are set up with that in mind. Of course, we will see that this is not always satisfied. Then the definition of the Newton method is actually an encapsulation of the Newton step. So where we do the updates. So this encapsulation happens here. And the advantage of the encapsulation is that when we write the Newton, we can focus on the layout. So the solutions are printed out in their full precision of 16 decimal places. The estimates for the forward and the backward error, these two norms, are given only with 2 decimal places. And the method may fail. So that happens here. We have failure. Last variable is true when we have exhausted the allowed number of iterations and have not reached the tolerances. Here is a very nice example. I think I took again the example with the E value. So you may recognize we have the transcendental constant E again to its fullest precision, most likely, because the last update is actually less than 10 to the power minus 8. And most importantly, you observe the quadratic convergence. There's also always a pleasure to see this. You see that the exponent actually doubles in every step, or almost doubles a little bit more, a bit less, and the exponent is negative. So a doubling exponent that is negative is an indication of quadratic convergence. Here is a very simple example, but still intersecting two circles can have some applications. So run the posted code and run it for adjusting here the two equations, f and g, to the equations for the circle. The question is, do you observe quadratic convergence? The answer will be yes, and in essence, this is a sanity check on how accurate, on how you have adapted and copied in into your Jupyter notebook the definitions for all the pieces that are posted as a Julia program. So again, the answer is yes, but show all your work. One can also say that suppose that you would know that you have here one decimal place is correct. How many iterations are necessary? You can actually calculate that without, or estimate that without doing any actual computations. So you go from -1, -2, -4, -8, -16. 5 steps. -1, -2, -4, -8, -16. So this is why this is justification for the default of 5, assuming that you start with 1 decimal places accuracy in your start point. The next equation, the next problem is a lot harder. So we have circles, so I should actually make a plot. So you have one unit circle centered at the origin, and then you see that the other circle is centered at 2 and also has radius 1. So these are two touching circles, and the answer will actually here be no. You will not observe quadratic convergence. So the drawing actually explains why this is a harder problem. If you run this, you will see that you may still observe linear convergence. Now we will not go into this. So analyzing multiple roots in multiple dimensions is a lot harder than we did for one equation. Last slide almost. So where do the Hessians then come in? Well, if you consider the application of Newton's method to minimize or maximize a function, then you will look at the linear system or the nonlinear system that is defined by the gradient. So because the gradients actually, the solutions of the gradient system now actually satisfy the critical points. So the candidate minima or maxima. You can also have saddles, as you remember from multivariate calculus. So we're solving a nonlinear system to which we will apply Newton's method. And here you see the point of this slide is actually to indicate that where do these symmetric positive definite matrices come in? Well, they come in from taking the Hessians of the forms that we try to minimize. So here, if you take the matrix of second partial derivatives, in a way you take the Jacobian of this, then you see that we have a symmetric matrix if the function is continuous. And if you are close to a minimum, so your function doesn't need to be entirely special, but if you're close to a minimum, then your matrix will be positive definite. All right, 6 lectures we have covered on linear algebra. There are 6 sentences that summarize the last 6 lectures. So we use matrix and vector notations. Condition numbers are very important to determine how hard it is to solve linear systems. In this, so if the condition number is too large, we can't really do anything anymore. But in this course, we care about numerically stable algorithms to compute here, as we have seen, an LU factorization. Iterative methods converge for diagonally dominant matrices if we solve a linear system, and they have a lower cost. With Koleski, as in last lecture, the LU factorization is done twice as fast. And in this lecture, we considered another iterative method in which gradients occurred. And then for general nonlinear systems, we have Jacobians and Hessians of general n-dimensional forms are actually a case where symmetric positive definite matrices arise. So that summarizes up our first introduction into numerical linear algebra.